to introduce our last but not least speaker. So Santiago, please enlighten us about these strictly positive polynomials in the boundary of the SOS code.
Yes. Okay. Thank you. Thank you very much, Veronica, Alicia, and Alexi, for organizing this wonderful session and for the opportunity to be here giving this talk here. I think, if I'm correct, I'm the last lecture in this session, if there is no bug in the system. And so this has been really a wonderful session, and I want to really thank Veronica, Alicia, and Alexi for organizing this. And I think I would like to ask from everybody a round of applause for the organizers. It has been really wonderful. I don't know how to do this virtually, but okay, I just click on. Okay, I will Thank you very much. I was a little involved in the organization, and I know how stressful it was to organize this in this all uncertainty, if it was going to be virtual or live in Buenos Aires, or how will it be, and a lot of things that were not clear when you started organizing, and you have to invite people without knowing how exactly was it going to be, and then without the change shift, how was people going to take all these changes, and well, it has been very stressful. So thank you very much, and everything went very smooth, and it was really a wonderful session. And so I think we're all very happy. So okay, I will start now with this. No, I'm sorry for all the problems, but thank you. Okay, so I will talk now about these strictly positive polynomials in the boundary of the sum of squares cone. This is a joint work with Marcelo Valletaro, both from the University of Buenos Aires. Okay. Yes, so Agnes has already talked about this, so I will go briefly through this. The fundamental problem we deal with is how to write a positive polynomial as a sum of squares of polynomials, and to know if this decomposition exists, and if it exists, how to compute it. So main application is that this decomposition gives a certificate of non-negativity. And for example, why do we care about certificates of non-negativity? One concrete application is if you want to minimize a polynomial over a region defined by polynomials or any region, then this is equivalent to finding the supremum of all the a of the real values such that f minus a is non-negative. So you transform a problem minimizing a polynomial over a region into computing some non-negative polynomials. So we're interested in this, in how to check if a polynomial is non-negative. So I define some sets. H is the set of all homogeneous polynomials of degree d in n variables. And P is the set of homogeneous and non-negative polynomials, and sigma will be the subset of sum of squares. So if you fix n and d, there are only a few cases in which these two sets are the same, positive polynomials and sum of squares, which are if n is equal to 2 or 2d is equal to 2, or this particular case, n equal 3 and 2d equal 4. And this was proven by Hilbert in 1888. This is very nice result, very complete result, because he proved both things, that in these three cases, both sets coincide, and in all other cases, they don't coincide. And the first example of a concrete polynomial that is positive or non-negative, but it's not a sum of squares, was given by Motzkin in 1967. So it is strange that so many years passed, because this was already known that such examples existed, but only in this year he could find it. And Hilbert proof is a little constructive, but very difficult to actually construct the example. So only this year it could be found. And he simplified, this is not like the construction of Hilbert. He found a very easy example that this can be checked very easily using some simple inequalities. And so we see that it's not the same sum of squares and positive polynomials is not the same. And so, but we are interested more in positive polynomials than in sum of squares. So why do we care about sum of squares? Well, if it's not, so we want to check if a polynomial is positive, but maybe it is not a sum of squares. So why do we care about sum of squares? Well, in general, you can use sum of squares for any polynomial, even if it's not sum of squares. You can approximate positive polynomials by sum of squares. So in general, any problem about positivity, you can solve by approximating polynomials by sum of squares. This is fundamental work by Parillo and Lasserre that give a lot of inputs to this theory of sum of squares. And the main importance of sum of squares is that it's much more simple to check if a polynomial is a sum of squares than to check if it is a positive polynomials. Agnes already presented this strategy. Is semi-definite programming, and any polynomial in degree 2D, if you want to check if it is a sum of squares, homogeneous of degree 2D, you can write, you can find such a matrix and get this matrix equality. So if you compute this product of matrices, you will get this polynomial for any value of A here. This is just equating. So you compute this product of matrices and you equate of all the monomials, the coefficients, and you get this only one unknown here. If it's a larger degree or many more variables, you will get many unknowns in this matrix. For any value, you get this equality, but it's not true that for any value, this will give you a sum of square decomposition. The condition that you need is that the matrix here is positive definite or positive semi-definite. So the condition is that F is a sum of squares if and only if there is a positive semi-definite matrix of this shape. And we define the ground spectrahedron of F to be the set of all these positive semi-definite matrices. And once you have this positive definite matrix, it's easy to compute this decomposition. You need to compute the diagonalization by congruence matrices, and the rank of this matrix will give you the number of polynomials, which is the same as the number of non-zero values in the diagonal when you compute this diagonalization. So this is simple to solve with numerical solvers. This kind of problems is semi-definite program. There are many numerical software to compute it, and you can compute even for very large size. You can compute this decomposition. So this is why we are interested in sum of square decompositions. And the problem we are interested in particular is to study the cone of sum of squares, and in particular to study the border, how to describe the border, what can you find in the border of the cone of sum of squares. So both sets are sum of squares, and non-negative polynomials are full dimensional convex cones. And the cone of non-negative is very easy to describe by equation. It's just the intersection of all these half spaces, that is the half space given by evaluation. But the sum of squares cone is much more difficult to describe, and we are interested in this. So there is one part that coincides with non-negative polynomials. This part where some polynomial vanish, or all the polynomials in the sum of square decomposition vanish, or the polynomial f has zeros, then it will be a common border with the border of the cone of non-negative polynomials. But there is another part of the border of sum of squares that consists of strictly positive polynomials. And this is what you are interested in study, to know what can you find there in this side of the border of sum of squares. So one thing you know, by what Agnes said, is that in this border, one thing you can check is it is in the border if it is not if there is no full rank matrix in the ground spectrahedron. So if you get a full rank matrix, then it will be in the interior. So one question related with what Agnes said is there are many examples found by Scheiderer that polynomials in the border of the cone of sum of squares that have rational coefficients but cannot be decomposed as a sum of squares of rational polynomials. And all these examples are in the border that coincides with non-negative polynomials. So all these examples have real roots. And so it's still unknown if you can find examples in the other border, in the strictly positive polynomials that are rational and do not allow a rational sum of square decomposition. This is still an open question, so it's very interesting to study this border. So there is a paper by Blecherman, which is, I really like, it's a wonderful paper. And so I will tell a little about this. What does he do? How do you study this border? So we first study a sequence of parameters. P1 and Pn is a sequence of parameters if the radical is the maximal ideal x1 to xn. And we define the Hilbert function. This is a very well-known function. It's the dimension of R over E over I in degree D. If you consider it as a vector space, it's the dimension of this quotient. So for example, if you take this ideal, x cubed, y cubed, z cubed, it's very easy to study Hilbert function. It's very easy to think about monomials. But you can always think when we put here x cubed, y cubed, z cubed as just a sequence of parameters of degree 3. In this case, the results are the same. So if you take this ideal, you compute the Hilbert function is these numbers. So for example, this last element is 1 in degree 6. This means that there is only one monomial that is not in I. And here it's very easy to compute. For monomials, it's very easy to compute. It's x squared, y squared, z squared. And another thing we know by this Cayley-Bacharach results theorems is that if you add any other polynomial to J, so you consider these 3, and you add anything else to this ideal, then this in degree 6 you will have a 0. So you will generate everything in degree 6. So this is very easy to check. If you add any other monomial that is not divisible by x cubed, y cubed, z cubed, then it will be a divisor of this, and you know that you will get everything in degree 6. But if you consider sequences of parameters, then it's not so clear. So the first result by Cayley-Bacharach is that for any sequence of parameters, you get the exact same Hilbert function if you have the same degrees and number of polynomials. And if you add any other polynomial, also you will get the result as long as it's a new polynomial, it's not in the ideal generated by the other 3, you will get 0 in the last position. So this paper by Beckerman, he uses this result to compute elements in the border of the sum of squares. So, or how to prove results of what can you find in this border. So let's suppose that we have this thing, that we have these 3 polynomials and one more, and we want to prove that it cannot be in the border. So how can we prove this? This is a proof by Beckerman. You take some functional in the dual of the space of polynomials, and you can define for 2 polynomials f and g, you can define this quadratic form ql of f to be equal to L of f squared, and the bilinear form, bilinear of fg is L of f times g. You can represent this by matrices, or this other way to represent it, you don't need to choose a monomial base, but if you have a monomial base, it's easier to think this with matrices. And now, if you take an element, a functional in the dual of the sum of squares cone, that is, you take an element that vanishes and on P and is positive in all other sum of squares polynomials, then you apply this to P. Yes, you apply this to P and this will be 0. So this means that QL of PI is 0 for all this PI. And this in particular means that all these 4 polynomials are in the kernel of Q. This follows because Q is strictly positive, or is a positive definite or semi-definite. So you only have that. You have that if you look at this product here, like in the definition of Q, you have that F transpose times Q times F is 0, but because Q is strictly positive, this implies that directly that Q times F is 0, and then this implies that L of any of these 4 polynomials times anything is also 0. And because we have seen that all these 4 polynomials generate all polynomials in degree 6, then you get that L is equal to 0. And this means that there is no non-zero linear functional that vanishes in these 4 polynomials. And then this means that this polynomial cannot be in the border. So this, I went through it very quickly, but it's very simple and very nice construction to prove that if you have 4 polynomials, you have a sequence of parameters and you add anything else, it cannot be in the border. So using these results, Beckerman proves that every polynomial in the border of the sum of squares cone that is strictly positive is a sum of exactly 3 squares, in this case, 3, 6. And in the case of 4 variables and degree 4, it's exactly the sum of 4 squares. So he gives a very concrete description of the polynomials in the border. So this was very surprising paper, very nice, because it's like nobody expected that there was so strict structure in these polynomials, and he found all these very concrete and very precise structures. So it's very nice. And other result that he proved for these cases is that these 3 polynomials are a sequence of parameters always, so they have no common zeros, not even complex zeros. So there are no real common zeros or no complex common zeros also. And so one question is what happens in general, and this is what we study in this work. And mostly we care about finding examples, because there are not many examples of what happens in higher dimension, higher number of variables, or higher degree. So we're mostly interested in what can happen by examples. And if we think about the same question, like what is the maximum number of polynomials that can appear in a sum of square decomposition, we can use a similar strategy as the one by Blecherman, but extend this strategy. And it's the same thing. You have to think how many monomials you need to generate all the monomials in degree 2D. So you start with this n monomials, x1 to the d, xn to the d, and you need to know how many more you can add without getting everything in degree 2D. And the question for monomials is very easy to solve. You consider the monomial that has the least number of divisors, which is for any number of variables is this monomial in 3 variables, x1 d to the d minus 1 times x2 to the d minus 1 times x3 to the square. This is not in I, and this has the least number of divisors. So if you don't include any of the divisors of degree d of this monomial, then you will not generate everything in degree 2D. So this means that if you add less than 3D minus 2 monomials to this ideal I, you will not generate everything in degree 2D. So this means that the maximum number of monomials you can have without generating everything in degree 2D is this dimension minus 3D minus 2 plus 1. So for example, for a concrete example, if you take n equal 4 and d equal 3, so one more, before for Blecherman was this case 3, 6, so we are extending like to the case 4, 6, then this monomial has 7 divisors, and then you can compute this number, n is equal to 20 minus 7 plus 1 is 14. So this means that if you have 14 monomials, then you will generate everything in degree 2D. And if you apply the same results, then the same construction as before, as here, or this construction that looks complicated, but it's not so complicated, then you can prove that anything that is in the border of strictly positive polynomials in the border of the cone of sum of squares is the sum of at most 13 squares. So everything here is done for monomials, but you can extend this to polynomials. So for polynomials, what we have just said is that you have these monomials and you add more monomials, then this number n gives the bound on the maximum number you can add. But this is not proved in general now. So you want to replace these monomials by polynomials by a sequence of parameters. And for some cases, it is known that you can replace this, but it's not proved for all cases. So this is based on a conjecture by Ottaviani Pauletti. It's called the OP conjecture. And in this paper by Blecherman, Sin, and Velasco, they prove that this conjecture by Ottaviano Pauletti implies this result for any number of variables and degree. So you can extend this result we have just shown for monomials to any degree and any number of variables based on this conjecture, which is only proved for degree smaller or equal to 4. What we did, we also deduced these results from Eisenberg-Green-Harris conjecture. This is a more general conjecture, so it can be more difficult to prove because this Eisenberg-Green-Harris conjecture is also, the statement is quite simple. It just says that if you have an idea that contains a sequence of parameters, and let's say all polynomials of the same degree, homogeneous, then there is a monomial idea with the same Hilbert function. So from this conjecture, we can also deduce this result. It's like all I have written here is more based on this conjecture, how to go from using this conjecture, how to extend from monomials to polynomials is just using this conjecture. So but this is also non conjecture, so you can also deduce from here, but both are not known. And this is more general, so in general, you could say that it's more difficult. The statement is maybe simpler, but it's still more difficult. So some examples we were interested is, okay, now you have bounds. The largest number of polynomials you can find is 13. For example, for the case n equal 4 and degree 6, and for other cases you also have examples and how to obtain concrete examples for these bounds. So we could do this. So based on the examples we already have, we prove, for example, for the case n equal 4 and d equal 2, we have some example by Blecherman. And if you extend the number of variables, then you can add all the monomials that are not divisible by the first variables. So if you add all these monomials and you add the squares, you will get the polynomial like this p1 square, p2 square, p4 square, m1 and ms to the square. If you add all these monomials, you will still be in the border. This we can prove by constructing a quadratic matrix that vanishes in these polynomials, but it's not a full rank. So this gives you the restriction we were looking for. So in this case, we can extend for the examples that were found by Beckerman to d equal 2 and d equal 3, but any number of variables, we can extend these examples. And for larger d, there are no examples for 3 variables. So if you have an example for 3 variables and any degree, then with this construction we do, you can extend this example to any number of variables. But you need to find some examples with the 3 variables. So for example, if you take this case, the case of 3 variables and degree 8, we could compute some examples that are a sum of 3 squares, so like a sequence of parameters. These kind of examples are quite difficult also to construct. Even Beckerman found a general procedure to construct these examples, but not all, but or maybe all, but it's not. So you can choose some particular values and then you can compute one example. So you can produce many examples, but they are quite difficult to produce. And we extend it, so we try to find examples in this larger setting. It's not so easy, but we could find this using some computations also. His proof is like more concrete because there are many more properties that are satisfied in these small examples that are not satisfied in general. But using some computations, we could produce this sequence of parameters in the border of 3, 8. But then you need to add 2 more polynomials to get the bound. And this we could not find like how to add these 2 more polynomials. So there is a gap, like if you have the theoretical bound and the examples, there is a gap of 2 polynomials. In any number of variables, we can extend this polynomial, so the bound will be always two polynomials missing. But we are working on this and doing some computations and numerics. We have some candidates to examples, but to prove these examples are always difficult to compute the concrete sum of square decomposition, and these kind of things are difficult to prove. So it's not a computing example, just you have the example and it's done. You need to really get some proof that these are working examples. So this was for the maximum number of polynomials. So the bounds predicted are obtained in d equal 3 and d equal 4, but for d equal 2 and d equal 3, but for larger d, still some gap missing. And also we're interested in the least number of polynomials. For this case, it's 3, 6, and 4, 4. F is always the sum of 3 and F is always the sum of 4, and this is the unique decomposition. But so one question is now, okay, maybe you can write it as a sum of 13 or some other numbers, but what is the least number? So these polynomials allow for a different number of polynomials in the decomposition. So we're interested in which is the least number of polynomials that can appear in a sum of square decomposition. There is some dimension count that you can do that gives you, for example, that this cannot hold in general, that all polynomials can be decomposed as the sum of n squares. Just by dimension count, you cannot get these bounds. But for example, for the case of 5 variables and degree 4, you could think by the dimension count that I'm not doing here, but that any polynomial is the sum of 5 squares. In this case, the dimension count could be that you can, sorry, I'm saying correct here. There's something, yes. So we have this example in 4, 4, and then in 5 variables, you can have a decomposition. We can find this polynomial that is the sum of 5 polynomials and it's not the sum of 4 polynomials. And we can also find this polynomial that is the sum of 6 squares, but it's not the sum of 5 squares. So this gives, like in this case, 5 variables and degree 4, the least number of polynomials is 6. So you need at least 6. And this is interesting because in this paper by Beckerman and Sturmfeld, another paper by Beckerman and Sturmfeld, they want to describe this as a variety. So every polynomial is the sum of 3 squares. This is the result they get. So this is included in the variety defined by the sum of 3 squares. So if you want to describe this border as a variety, then you need to know how many squares you need to consider. And okay, this is what we are studying. So in this case, you need at least 6 squares. So this is a concrete example. And proving this is also not so easy to prove that you have a polynomial, a sum of 4 squares, and you want to prove that it cannot be written as the sum of more polynomials or less polynomials. This is not easy. So in this case, for example, we have another example for variables and degree 6, this example, and here we can prove that is the unique decomposition. We construct a quadratic form Q that is positive definite that had exactly this kernel, and this gives the proof that is a unique decomposition. So basically, these many examples. And all these examples were more or less expected. Like you can construct these kind of things, even they're not so easy to construct or to prove, were more or less expected. But one unexpected result. So when we discuss this thing with people that are working in this, is like all the other things, okay, the examples were not known, but maybe more or less expected. But this was very unexpected result, that the unexpected example that in more variables or higher degree, you can find examples that have less than n squares. So we could compute this example that I will finish with. This is here in the last box. In the case of 6 variables and degree 4, we could compute a polynomial that is the sum of 5 squares. So less than n equals 6 is 5 squares. And this polynomial is in the border of the cone of sum of squares, and it has a unique decomposition. So this is the only decomposition. It can only be decomposed as the sum of 5 squares. So in this case, because all the other examples were known, you start with a sequence of parameters, and then you consider a restriction so that this sequence of parameters gives a polynomial in the border. But here you have less than n polynomials. So if you have less than n polynomials, one consequence is that these polynomials will have some common complex roots. So this is what was unexpected, that the construction in Blechermann is based on, if you have something in the border, then you will find a sequence of parameters with no common roots. And for this case of degree 6 and 4 variables, we find this example that has common roots, complex root, obviously, because if it has common real roots, then it will not be strictly positive. But we have a find example with complex common roots, and it's the sum of less than 6 squares. So basically, what we're finding is that the situation is much more complicated. If you go from the cases of 3, 6, and 4, 4, you will get many more things. So everything that's satisfied there for 3, 6, and 4, 4, you cannot expect to be satisfied in the larger cases. So this is basically what we are doing and studying and trying to get more examples and properties. So yes, thank you very much. I finish here. It's only some references for the work I've been mentioning, and thank you very much.
Thank you, very nice. So I have a question. How did you compute this last example with the 5 squares? How did you find it?
It's always, you start with some example that, for our case, so you start with some example that you know. For example, this example, we start with the example in 4, 4. So 4 variables and degree 4. This was already known. This is in the paper by Blechermann. Then you add this polynomial x5 to the square, and then you have to check if this polynomial is really, if it is in the border or not. So the problem of checking if a polynomial is in the border or not, you can do this numerically using this first thing we mentioned, that you compute using these numerical solvers, you compute the matrix of the highest rank. So if you use numerical solvers, you can use some condition, maximize some condition that will find an example of the maximum possible rank. Because this is like interior point method, so it will find something that is in the largest interior, something like that. If it's interior, by some reason it implies that it's the largest rank. So if you do this, you compute the composition matrix with the largest rank, and it coincides with the same rank you started, and it's the same decomposition. This means that this was the unique decomposition. But this is only numerically. So numerically, you can do many experiments. It's very quick. But then once you get one experiment, one result from the numerical experiment, so you compute the matrix, and it's not full rank. It has smaller rank. Then okay, this is a good candidate. And then you have to do some proof, and you have to construct a matrix Q that is strictly that is positive definite, that vanishes in these 5 polynomials, and this way you can compute its decomposition. And then this, just from this example to here, we replace x5 squared, we replace by this polynomial. So this was just a trick on how to produce complex roots without violating the unique decomposition, and just by this was more like just trying different things until we could find it. But this is also easy to prove. Once you prove that the first one has unique decomposition, then it's also easy to prove that also this has a unique decomposition. So it's both techniques. We have numerical techniques to test some examples, and then we have some symbolic tools to prove the examples.
But this result that you showed me, that if you are in the boundary, then the maximal rank cannot be full rank.
Yes.
But this only goes in one direction, right? So this gives you a hint that this could be the case if you don't get maximal rank, but you're not sure.
So these polynomials are already strictly positive, like this example. So this is already strictly positive because the only common root is 0. So you know that this is already strictly positive. So if you have a strictly positive polynomial and you know that there is no full rank matrix, then this is in the border, yes. So if you are in the interior, then you will always find a full rank matrix. So yes, so these two conditions, that there are no common roots and there is no full rank matrix, these two conditions imply that it is a strictly positive polynomial in the border of the sum of squares cone. Yes. So
very nice.
Yes, yes.
Are there any other questions for Santiago? Not now. I see something in the chat, but maybe it's a message for me. Yes. Okay. So thank you very much. Thank you all for your participation. We will stop the recording now and we